First of all, what is this extended stellar parameterizer for cool stars? Actually, what it did in DR3. In DR3, the code computed the chromospheric activity index from the calcium 2 infrared triplet lines in the RVS spectra. It is supposed to do something else, but that will be for future data release. But in the data release 3, this is what we had. And this was computed for stars with the G magnitude less than 13, effective temperature between 3000 and 7000 Kelvin, log G between 3 and 5, metallicity between -0.5 and 1.0. And this led to an activity index estimated on about 2 million stars, which I believe is the largest catalog so far at the moment. Sorry. Okay. So how did we derive this index, and how this index is defined? As you may know, there are several ways of giving the activity index from a star. For practical reason, we choose essentially the excess equivalent with the factor with respect to a radiative equilibrium synthetic spectrum. So essentially what we have is here you have in black the observed spectrum in the 3 lines of the calcium infrared triplet. In red we have a model spectrum taken at the parameters of the star, which means effective temperature, log G, and metallicity. The spectrum is an interpolation of a grid of Marx spectra treated as they were observed by the RVS instrument, which means that the line spread function of the instrument is taken into account. So essentially, we build up the ratio spectrum, so the observed spectrum divided by this template, this interpolated spectrum, which is taken as a template, and we integrate this over 0.15 nanometer. In this relationship, R is the ratio between the flux at wavelength lambda and the corresponding flux at the continuum. So it's continuum normalized spectrum. Okay. So in essence, activity index is given as the excess equivalent with factor in the core of the lines, and it is a proxy of the chromospheric activity or mass accretion in pre-main sequence star when mass accretion is present. As a template, we take a radiative equilibrium model spectrum as an interpolation of a grid of Marx synthetic spectra, using the effective temperature, log G, and metallicity either from the output of GSP spec or GSP FOT. In DR3, the criterion is that we take the result from GSP spec if they are present. If they are not, we take the result from GSP FOT. Rotational broadening is taken into account, so the template spectrum are rotational broadened according to the V-broad parameter provided by CU6 that analyzes the RVS spectra, that reduce the RVS spectra. And as I said, the interpolated rotationally broadened synthetic spectrum is taken as a template spectrum. The output is the mean alpha over the 3 lines and is stored as activity index ESP-CS in the astrophysical parameters table, and is given in units of nanometer. We also evaluate uncertainties by propagating the pixel standard error, ignoring theoretical uncertainties. And this is given as the activity index ESP-CS uncertainty parameters, again in nanometer units. And this is present in the astrophysical parameters table. There is a flag that indicates which source was taken for the input parameter of for the model spectrum, and this is and this has 2 values essentially: M1, which means that we have taken the effective temperature log G and metallicity from GSP spec, or M2, which means that we have taken the effective temperature log G and metallicity from GSP FOT. Now, before I go ahead, I should say something about the usage of this index and a few warnings about the usage of this index. For several reasons, we decided to provide alpha, which is a raw quantity. And I must stress that this is unsuitable for comparing the activity in stars with different effective temperature log G and H. The reason is that the observed equivalent width depends on a complex interplay between the photospheric radiation and the chromospheric plasma. So to make a long story short, essentially, when you look at the excess equivalent width of the line, the same, say, alpha value, according to the definition I gave before, corresponds to very different chromospheric heating if the effective temperature in particular is very different. Also, to a lesser extent, for different log G or metallicity, more metallicity, I must say, that log G. But when the effective temperature is very different, to the same alpha value, you have a very different regime of chromospheric heating. However, alpha can be used in combination with the other fundamental parameters to compare chromospheric activity in a large range of effective temperature, log G, and metallicity, or discriminate chromospheric activity versus mass accretion. So again, I stress the point, we give this alpha, which is a basic raw quantity, which the user can use as they wish, but the users must be careful about the fact that this alpha cannot be used to compare very different stars. Something else must be built from this alpha. And we give a very simple recipe for doing that. Also, alpha can be negative, of course, both because of the uncertainties, but there is also a physical explanation for some negative value of alpha. That is that when you say increase the activity level, the chromospheric plasma temperature from no chromosphere at all to some activity from the chromosphere, what you have is that you first increase the residual of the line with respect to the radiative equilibrium template, and then the line, by increasing the heating of the chromosphere, the line residual increase, that we have this fill-in of the line, and the line may go into emission, either in the core, or the whole line, in extreme case, can go into emission. So this alpha can be also negative, and don't be scared about it. There are reasons for that. Now, what is the recipe if you want to compare activity in stars with very different effective temperature? In the same way as has been done since the 80s for the H and K ultraviolet calcium 2 lines, one should use the chromospheric flux, which we call F prime here, divided by the bolometric flux, which is indicated as sigma T effective to the fourth here. The chromospheric flux is the difference between the total flux you receive in the line minus the photospheric contribution. As a photospheric contribution, we are assuming a model in radiative equilibrium. So since we define since we give alpha, which is an excess equivalent with factor with respect to the radiative equilibrium model, the excess equivalent width, defined as the difference between the normalized spectrum observed and the normalized spectrum, the theoretical continuum normalized spectrum, is related to alpha by this relationship. You need to take R lambda in the core and multiply this by alpha. And if you want the flux, the chromospheric flux, you have to multiply the flux in the continuum by this delta equivalent width, the excess equivalent width. And therefore, in our, according to our definition, you have to multiply this flux in the continuum to the residual in the core of the line times alpha. So this R prime ERT is this quantity in bracket time alpha. This depends only on say known continuum flux that we may take from the model. And the R lambda in the core in the radiative equilibrium spectra that we can compute, and also sigma T effective to the fourth is something that we can compute. So we approximated, we fit this quantity, the logarithm of this quantity between brackets, and we provide a polynomial relationship linking the effective temperature to this factor between bracket here. The coefficient can be found in the accompanying paper, Lanzafame et al., that I think will be officially published in 2023, although has been out as an archive paper from many months now. So you can use the alpha we provide in the table. You take the logarithm of this alpha, you add this quantity according to the effective temperature, and you have an index, the logarithm of R prime IRT, that you can use to compare activity in stars with very different effective temperature. So we provide the raw quantity and a receipt for computing an index that can be used for comparing in a large range of effective temperature. But of course, if the user want to do something else, they have the raw quantity and can do something different from what we provided. So having said that, let's look a bit at the validation of our results. First of all, a first look at the spectra in different conditions. In the upper two panels, we have a relatively low level of activity, and this is how the comparison between theoretical and observed spectra look like, and the ratio spectrum -1 is below, and in yellow here you have the area that has been considered for the integration, and therefore the activity index provided in the table. In the bottom panel left here, we have a case of an active star, and you see how this excess factor arises with respect to a quiet star. And in the bottom right panel, you have a case of a known pre-main sequence star in which the core of the line goes into emission, and here you have the correspondent alpha value here is reported here together with the fundamental parameters of the star, the source of the spectrum, and the source of the input parameters, and the value of Wieseni that was adopted to broaden the theoretical spectrum. The distribution of the alpha value look like this, and we divide it by, in this case, we concentrate only on, we show only the distribution between 4,000 and 5,000 Kelvin. Here for logarithm larger than 3.5, and for, in this case, for a logarithm of G smaller than 3.5. This outlines a couple of things. When the star is a fast rotating star or an active star, in DR3, GSP spec did not provide essentially parameters. So in case of active star, a accreting star, or a very active star or fast rotating star, the input parameters comes essentially from GSP FOT. And in this case, the distribution is skewed toward high value because, of course, of the presence of accretion or quiet or active, chromospherically active star. On the right panel, on the other hand, we have the same distribution for low log G, which means some evolved star, more evolved star, in which the activity level is in general quite low unless there are special reasons for having induced activity in the star, like stars in binary systems in closed binary systems like RS-CVN stars. So you see here the distribution around 0, it is quite nice, and this gives essentially an idea of an upper limit for the uncertainty we have in the activity index alpha we provided. We can compare with the extensive catalog of R prime H and K, so the same index but computed using ground-based data in the HK ultraviolet line in the calcium. And for this, we used essentially two sources. One is the Boros-Saikia paper in 2018, which is a collection of R prime H and K plus some measurement done with the ARPS instrument. And we have a nice, when we consider the R prime IRT computed using the GSP thought output as input, we have a quite nice Pearson coefficient around 0.5 and a good linear relationship. This is essentially the fit. And another source is our computation on the archive Ferros spectra, which give a quite nice Pearson coefficient of 0.73. The gray points are index calculated from the input of GSP spec, which take low signal to noise in the R prime IRT, so there is a larger dispersion, and the correlation is a bit lost. But when we consider higher level of activity, we have a nice correlation between the R prime ERT and the R prime H and K. The various color here, the open square here indicating the Boros-Saikia data, and here the color indicates red is, as we shall see in a moment, is the accretion regime. Blue is the very active regime, and the yellow is the low active regime, as we shall see in a moment. And here it is when we...
Sorry, Alessandro, I check with the time. It is 11:40 now.
Okay. How much time do I have?
20 minutes.
Okay. When we plot R prime versus T effective, we have a nice distribution, which is not very different from what was found recently in the literature from Boros-Saikia in 2018, but of course with much sharper details and statistical significance. On the left, we have the results for log G larger than 4, and on the right, we have the results for log G less than 4. It is obvious here that we have a very high activity branch, and this is essentially, as we shall see in a moment, these are all pre-main sequence stars. So here we have a mixture of high chromospheric activity and accreting star in this part here. As we shall see in a moment, this other branch here is active star, very active star in the main sequence, mostly, not only, but mostly. And here we have all a bunch of inactive stars. It is very interesting what happens here at the boundary of fully convective regime, where we have few stars here at this boundary, and essentially a quite different distribution in the level of activity when the star is fully convective. For the low surface gravity sample, we have essentially here all inactive star, apart from a high branch here that probably comes from RS-CVN systems mostly, or maybe also some pre-main sequence star, as we shall see in a moment. So if we project this distribution in one dimension, just not distinguishing for different effective temperature, we see mostly three peaks, say, in the distribution. This peak here corresponds to accretion, as we shall see in a moment. This corresponds to high activity, and this may say that this is low activity. And this minimum here corresponds to what it has been suggested in the literature many years ago, which means a gap which was named Captain Gap. But we have the possibility of digging into this this distribution, and we see here on the left the result for log G larger than 4, on the right the result for log G less than 4. In gray we have the general distribution, and here we have the more detailed distribution. And in blue here you have the temperature higher than 5,000, and in red the temperature lower than 5,000. So you see that below 5,000 there is essentially no minimum, there is a unimodal distribution of stars in chromospheric activity, and this bump here is due to the pre-main sequence star with accretion. When you combine the star with effective temperature below 5,000 and higher than 5,000, you have this double peak here. If you consider star with log G less than 4, you see no double peak, essentially. The distribution are unimodal. The fully convective regime appears unimodal as well. Why I say that those stars correspond to accretion or high chromospheric activity? Because if you consider the distribution, the position of these values in the color magnitude diagram, for clarity, I had to split, to bin the data in R prime IRT greater than minus 4.8 or less than minus 4.8, and I had to take a random sample because otherwise you would see nothing. But you see that for high value of the R prime, we have stars that are here in the subgiant branch where we expect active RS-CVN star, or here in the region where we expect to have binary stars or a pre-main sequence star. So this branch here is very populated, and here at low temperature, red colors, we have a bunch of stars here. When we decrease when we consider a low activity level, you see that the stars are in the single star main sequence, mostly here. They concentrate mostly here and are a bit on the upper envelope of the main sequence single star. You see here we have the active star have disappeared at red, very red color. And again, when we go to very low level of activity, we see here these are on the low part. We see the low part of the main sequence populated, as well as the subgiant region is again populated by low level of activity stars. So it makes sense from what we know of the evolution of the magnetic activity, of the chromospheric activity and accretion. All this makes sense. Another thing that makes a lot of sense is the correlation with the rotational modulation that we provide within the CU7, the variability coordination group, coordination unit. So when you compare the amplitude of the rotational modulation with the R prime IRT, essentially what you are doing, you are correlating the chromospheric activity to the photospheric activity. The photospheric activity due to the presence of dark spot, and the larger the spot, the larger the surface area covered by the spot, the more active is the star, the more active is the photosphere of the star, and of course you expect that this activity is reflected somehow in the chromosphere, as it does, because you see here in color scale the amplitude of the rotational modulation, and you see that the more active star have the largest rotational modulation, and the less active star, the less chromospheric active star, have a lower rotational modulation level. Let me dig a bit more into this issue of rotational modulation. In DR2, we came out with a large database, or with a larger data set on rotational modulation. And when we see this data in the amplitude of rotational modulation versus period, in this case is the Rossby number, which is related to the period of rotation of the star, we found some clustering in this diagram, which we called high amplitude rotator, ultra fast rotators, or low amplitude fast rotators here, and low amplitude slow rotator here. And this is essentially the tip of the non-saturated regime, where rotation and amplitude goes together, are correlated, while this part here is the saturated regime, in which the dependence of the amplitude with respect to the period is not very sensitive, is not very high. So when we specify, when we look at where these sequences are in R prime versus the effective temperature diagram, we see that the high amplitude rotational modulation star, which are T Tauri star, prime and sequence star, are actually in the upper branch where I said there are T Tauri, prime and sequence star, accreting star. If you do a cross match with SIMBAD, you see that the T Tauri stars, the prime and sequence stars, sit essentially in this branch. When we plot the low amplitude, slow rotator sequence, they are all in this region. So from here on, from here down, the activity, the index is essentially chromospheric activity. So this branch is accretion, mostly accretion, but there are also some RSCVN here. But here you have just chromospherically active star. The nice, the puzzling thing about it all is the low amplitude fast rotator population, the low amplitude fast rotator regime, which are fast rotators. So essentially, being fast rotator, we expect high activity, but surprisingly, they have low photospheric and low chromospheric activity. And this is something that we like to understand, a puzzle that we like to solve. And this is very interesting for understanding magnetic activity in stars, especially in very young stars close to the zero-age main sequence. So I just conclude here, maybe with 5 minutes margin with respect to the respective time. So what ESP-CS has provided is a chromospheric activity index for 2 million stars. This is accompanied with rotational modulation data for 500,000 stars from CU8. So altogether, we have unprecedented details on magnetic activity regimes. There is an evident correlation with the internal structure. Just consider, for example, what we have on one side or the other side of the fully convective boundary. There are intriguing issues on fast rotating stars with low magnetic activity indicators, and this information, I believe, is key for exoplanet hunters, since it gives a measure of the possible radial velocity jitter that exoplanet hunters may have in their research for exoplanet, especially when they are of almost planetary mass. And this is it. Thank you very much.